assume that you're okay. Yeah. I think people are slowly getting in. So while that's happening, we just remind you of what we were doing yesterday. And we did section 1.2 where we introduced the distance formula and basics of vectors. This is nothing really groundbreaking there. We defined a vector and we looked at what it means by adding two vectors and scalar multiplication, and when two vectors are parallel, that is when a vector is a scalar multiple of the other. We also started 1.3, and that's where we saw most of the more important things. Okay, we looked at the dot product of two vectors and also the angle between vectors, and we're going to talk a little bit more about those two things today and finish off the problems in the worksheet, and then we'll start chapters or sections 1.4 and 1.5. Okay, that is our objective for today. We'll finish those two sections tomorrow. So this week's quiz, if you look at worksheet number 2, I've written there that quiz number 1 will cover worksheets 1 and 2. So we'll keep in our material kind of organized in terms of this worksheet so that it's easy for you to study as well. Okay, so. All right. Before I start anything, we make sure that can people hear me okay online, or somebody will have to either unmute or, all right, good. Can people see everything properly? All right. Okay, so let's we just write down what we were doing with this. Okay, so dot product of two vectors. If you have, say, u equal to u1, u2, u3. Let's just talk about R3. I think the textbook has written it in terms of a general vector in Rn, but then since we are going to mostly deal with R2 or R3, I'll just write it for R3. So if u is this and v is, say, v1, v2, v3, then u dot v is a number, not a vector. Okay, it's a scalar. That's why it's called a scalar product. That's u1, v1 plus u2, v2 plus u3, v3. Okay, now that is a number. It could be positive, it could be negative, it could be 0, but that's a number. Okay. And if you have these two vectors, u and v, with an angle theta between them, we could use the dot product of the two vectors to find the angle that is covered between these two. Okay, so cosine theta is dot product divided by the magnitude of u times magnitude of v. Again, those, if you recall from yesterday's lecture, this is the length of u or the magnitude of u, okay, which in this case would be square root of u1 square plus u2 square plus u3 square, and the magnitude of v is the square root of v1 square plus v2 square. So no matter what the components of each vector is, okay, that the length of the vector is always a positive number. It's equal to 0 only if it is a 0 vector. And if u1, u2, u3, all of them are equal to 0, then the magnitude of u is 0, but otherwise it's always a positive number. Okay, so that will give you the cosine of the angle theta, and then theta is the inverse cosine of the arc cosine of that number. Okay. Again, that's a dot product as a number, so there is nothing weird in terms of dividing those quantities, even if it looks bizarre with vectors in the two terms. So that's where we stopped. So let's, if you don't have any questions, let's just finish off that worksheet, and then, so if you can, I don't know if you can access Canvas from here or no. Sorry to kind of put you on a spot there. I can write the problems here if you want, or you could, worksheet number 1. So we did 1A yesterday. We're going to do 1B, C, and 2 right now. Okay. So whenever I write WS into the worksheet, the PDF should be there on Canvas under modules, so you can just pull it out. For these problems, I could write it down. For longer problems, you might want to just keep it next to you. So you have two vectors, u equal to, you can do it along with me so that we could both compare our answers. So we have u equal to 3i plus 2j minus k, and v equal to I plus 4j minus 5k. So the question is just to find a dot product. I don't think there was any other part to that question. Okay. So those of you who don't like the IJK notation, just keep in mind that this is the same as a vector 3, 2, -1. Did you leave some cash behind? 1, 4, -5. Okay, so either way, right? Whichever notation is convenient for you. So u dot b is just going to be 3 plus 8 plus 5, not 3 comma 8 comma 5. And that's 16. And 1C looked a little asymmetric. I minus k and j minus k. You should be careful when you're dealing with vectors with missing components. You just need to fill in a 0 there, okay, so it's not a vector in R2 now, right? So this is 0, this is 1, 0, -1, and this is 0, 1, -1. So that's the advantage if you write it in the component notation, then it's easy to kind of see it, which term multiplies what. So u dot v is equal to 0 plus 0 plus 1. Does it make sense? There is no restriction on what the value of a dot product could be. It could be positive or negative or 0 or 1 or pi. Okay. That depends on the components of the vector. So. Good workout for me. All right, let's also quickly do number 2, I think. Find the angle between 1, 2, 3 and 3, negative 2, 1. So if you don't think about dot product, this might look like a weird question. It doesn't tell you find the dot product, it tells you directly find the angle. Okay, so that's where we need to make that connection that the angle between two vectors, whether it's R2 or R3, it has to do something with the dot product of those two vectors. So if you name this as U and this is V, then the cosine of the angle theta, which we derived yesterday, is U dot V divided by the magnitude of U times magnitude of V. And since we have done enough of dot products by now, this dot product is going to be just 3 minus 4, which is negative 1, plus 3 is 2. Right? 3 minus 4 plus 3. Yep. 6 minus 4. The square, the magnitude of U is going to be the square root of 1 square plus 2 square plus 3 square. That is the square root of 14. And this is also the square root of 14, which is 2 over 14, which is 1 over 7. So theta is going to be the inverse cosine of this number here, 1/7. I don't think that's a famous angle. You have to look up the calculator and see what it is. So theta is inverse cosine of 1/7. And who is going to help me with this? All right, I already have an answer, 81.79 degrees. What do you get? Yeah, just be familiar with what your calculator can do. Don't wait till the day of the quiz to figure out, oh, where is that cosine function? So just do it early enough so that you know where things are. You can also use your cell phone, I think. I mean, most of the cell phone calculators should have this feature of finding inverse cosine. And so, okay. All right, so that is where we stopped yesterday. All right, if you don't have any questions, let's do a few more things with this. So all those questions were from the worksheet. Okay. Let's just look at this thing a little bit more closer and see what other information it can provide us. Okay. So if you write cosine of theta equal to U dot V divided by the magnitude of U times the magnitude of V. Okay. You don't read it as absolute value. It represents the length of the vector, so it's a magnitude or the length of the vector. Okay. And I hope all of you are familiar with the value of cosine in each quadrant. Okay, so the value of cosine, the first quadrant is positive and the second quadrant is negative as you go from here to here. So it starts from 0 degrees, 90 degrees, 180 degrees. Okay. So two vectors, when you talk about the angle between those two, it could be perpendicular or it could just go in opposite directions or it could just go in the same direction. Okay, so that is the range of the angle theta. So theta goes from 0 to 180 degrees. Okay, so 0 if it is just lying on top of each other in the same direction, 180 opposite, and in between is 90 degrees. Can we just get that information based on this expression here? Okay. If you look at this number here, this is always positive because it's the sum of the squares, square root. This is also always positive. Unless it's equal to 0, okay, those two numbers are always positive. So the sign of cosine of theta just depends on the sign of the dot product u dot v. The cosine of theta is positive if u dot v is positive. Okay. And when you say cosine of theta is positive, that means your theta is going to be in the first quadrant. In other words, your angle theta is going to be between 0 and 90 degrees, not equal to 90 degrees, maybe 89.999999. And cosine of theta is negative if u dot v is negative, okay, that is strictly less than 0. That's possible if you take two vectors whose components kind of add together to give a negative dot product. Okay, that's okay. And in that case, your angle is going to be greater than 90 degrees. So theta is in the second quadrant, or theta is going to be between 90 and 180 degrees. Okay. I'm still not hitting that 90-degree thing. That's a special angle. Okay. So it could be 0 degrees if it is in the same direction on top of each other, 180 degrees on the opposite side on top of each other. Of course, such an angle is called an acute angle. And this angle is called an obtuse angle. So just based on the sign of the dot product, if u dot v is positive, that means theta is acute. And if u dot v is negative, that means theta is obtuse. Just based on those signs, we don't have to find the magnitude or the exact value or anything, just that information about whether it's acute or obtuse based on the sign of these numbers. Okay. But the more important thing is what is happening in between those two. Okay. This is where vectors have a special relationship with the dot product of those two. So if u dot v is equal to 0, then cosine of theta is 0 and theta is equal to 90 degrees. It tells you a condition for two vectors being perpendicular. Okay. So very important. I don't really care if the angle is acute or obtuse. You know, that's something you can measure, but the perpendicularity is a very important property of vectors. Two vectors u and v are perpendicular. There are other fancy words for this: orthogonal, normal. Okay, all these are the same thing. Two vectors u and v are perpendicular or orthogonal. If you take linear algebra, you'll keep on saying orthogonal vectors or normal vectors, if and only if u dot v is equal to 0. Because if that happens, then theta has to be 90 degrees. U dot v equal to 0 because cosine of 90 degrees is equal to 0. And that happens only if the dot product is equal to 0. That's a necessary and a sufficient condition for two vectors being perpendicular. Okay. Very important. Even if you don't know about acute and obtuse angles, you should know, but okay, the more important one is this. So yesterday we talked about two vectors in parallel, that is if they are scalar multiples of each other. Okay. This tells you a condition for being perpendicular, that is the dot product of those two vectors is equal to 0. Okay. Exactly. So just to check this out, okay, so example, given u equal to 2, -3, -4, and v equal to 5, 1, 10, okay, 1, 10. Is the angle between u and v acute, obtuse, or right? 90 degrees is right angle. What do? You take a graph paper and carefully draw these points and measure the angle, or is there a quick way of doing it? How do you do this? Yeah. Yeah. Just take the dot product and check if that is positive, negative, or zero. Okay. Be very unlikely to get it zero because I just wrote a couple of random vectors. So I should be really lucky to get it equal to zero. But let's see. This is going to be 2 times 5, 10, -3, -40. That's negative, right? That's all we care about, because our question is to determine if it's this, or this. It's a trichotomy, cannot be both at the same time. So it's negative, that means theta is obtuse. What is that angle? For that, you have to go through that process there. You have to find cosine of theta equal to all that and find the inverse cosine, but that's not the question here. So if you understood this concept of whatever I wrote there, the very important thing, can you do the next question in your worksheet? Question number 3. It's kind of an indirect way of asking the same concept. Find the values of A so that those two vectors are perpendicular to each other. How do you do this question? It seems like a weird thing, yeah? Yes. So just make use of the concept I wrote there, right? If the only condition in which the two vectors are perpendicular is if the dot product is equal to 0, and you know how to do that, right? So A 1 2 dot 2 1 A equal to 0. So 2A plus 1 plus 2A. So that's 4A plus 1. So A is -1/4. Okay, so just to make use of that concept of two vectors being perpendicular. All right. It's not too bad. Any questions about the concept of angle between two vectors and dot product? Nope. One last thing from section 1.3, orthogonal projection. This is a concept that you might find useful in other classes. maybe not in calculus 3, but when you take engineering classes where you have to resolve a force into components and so on, okay, that is where this concept is useful. It's also useful in some of the computational techniques they use these days for complicated problems. So this is the setup of the problem. If you have one vector here, okay, say again, it's in a general context of R2 or R3. It should work in all those cases. So F is any vector. So R2 or R3 or even higher dimensions, but we are just trying to limit ourselves to R2 and R3. And suppose we have another vector here. Let's name this as F and this is V. Sorry about that. That way it's easy for me to kind of look at the picture carefully. Okay, so this is some vector F and this is another vector V. We are trying to find a component of F which is along V. Okay, so you can think about this as a force. What will be the component of the force which is in a certain direction? Okay, so we are trying to resolve a vector into its principal components. So let's call this as, let's just drop a perpendicular line from there to here. Okay, so this is 90 degrees. So let this be FV. So FV is it's this length here. Okay. It's a projection of F onto V. So it's the component of F. Which is along V, which is the same as saying which is parallel to V. And there's also a component here which is perpendicular to V. Okay, so let's call this as Fn, where n stands for normal. And since I'm writing it here, let me just write it right below it. So Fn is the component of F. Which is perpendicular to V. Okay. Now, based on our discussion so far, the first thing that should remind you is that the dot product of Fn with V is equal to 0. Okay. Because that's what we just saw, right? Two vectors are perpendicular if the dot product is 0. The other thing, which is parallel to V, means you can write Fv to be some scalar times V. From yesterday's discussion, you know that two vectors are parallel if one is a multiple of the other. Okay. Now, these two components must add together and give you the net force of F. Okay. This Fn, which is the perpendicular component, and Fv, which is the parallel component, they should just add up and give you F equal to Fv plus Fn. But what are these things? How do we calculate Fv and Fn? Okay. We only know that Fn is perpendicular to V and Fv is parallel to V, but we don't know what exactly the length of each of them would be. Right? So to do that, we'll just do a dot product of this whole equation with respect to V. So do dot product with, it's a clever trick because we know that the Fn dot V is equal to 0, so that kind of eliminates one of them. So you have F dot V equal to Fv dot V plus Fn dot V. Because we have two things to find, and there is no way we can find both of them at the same time unless we eliminate one of them. And to eliminate Fn, we just dot the entire thing with respect to V. As long as you do it on both sides, that's perfectly fine. Okay. So this term is equal to 0. Now we are left with only one of them. Okay. Now don't cancel the V because it's a dot product. It's not your regular multiplication. So Fv is F dot V. And you know that Fv is K times V. So F dot V equal to K times V dot V. So the dot product on this side equal to K times another dot product on that side. The dot product is always a number, so we are not looking at anything unusual here. So K is the scalar given by F dot V divided by V dot V. Okay, that's a scalar. It looks complicated because you have dot product, but you're just dividing a number by a number. So this is that factor that is going to stretch or compress the vector V depending on the vector F. So this gives you Fv equal to F dot V divided by V dot V times V. If you just plug it in there, yep.
So when we're finding the orthographic, or we're asked to find the orthographic projection, we're just finding the scalar.
Yes.
That would allow us to solve the sub F.
Yes. So the orthogonal, not orthographic, orthogonal projection. Right? Yeah. The orthogonal projection is that particular scalar that is going to scale this and give you this vector here parallel to V. Okay. So this is the orthogonal projection of F onto the vector V. And then you can find Fn because you're given F, you know Fv, and Fn is going to be F minus Fv. That might look like a trivial thing, but then this is a unique decomposition of the vector F into two components. Okay. There is only one pair, Fv and Fn, that is going to make that happen. So Fv is obtained this way, and then Fn is just F minus Fv. So once you have Fv, you can write F equal to F minus Fn equal to F minus Fv, because F was the sum of those two, and that will give you the second component, which is perpendicular to V. Okay, so that part is pretty easy. So now we have got both the components, one which is parallel to V, the other one which is perpendicular to V. Okay. So I'll do an example, and then we will do the example in that worksheet, which is the only one remaining. Any questions about this? Again, the derivation is not something for you to remember from an academic point of view, but I don't want to keep writing things randomly, so that's why I always do things from scratch. Okay. But do you have any conceptual questions about orthogonal projection? Yes.
Couldn't you also find the orthogonal projection using the angle between them and then treating one of them as like sort of x-axis?
You could do that using the angle, but then the angle takes its own measurement. So this one keeps it kind of nice. The dot product is a straightforward calculation, right? If you do in terms of angle, then you need measurements of the angle, which makes it complicated. Okay, the whole assumption is that angles are not easy to measure in general. So yeah, that's a good question. I mean, you could do it in multiple ways, but I think using the dot product and getting the scalar is the most straightforward approach. Any questions from the online community? All right, so let's do a quick example. Let F equal to 3 to -4 and V equal to 1, 1, 1. Find the orthogonal projection of F onto V. Some textbooks write this orthogonal projection of F onto V like this projection F V. It's the same thing. Okay. Especially in linear algebra, they use this notation, projection of F onto V. So it's the same concept. Find the orthogonal projection of F onto V and then write F as a unique combination of two vectors, one which is parallel to V and one which is perpendicular to V. It's a long question. All right, so we will do this and I'll let you do the one of the worksheet later yourself. Okay, that's after I do this. All right, so the magic thing that we need to keep is this K and this FV. Okay, everything else can disappear for now. This is the orthogonal projection of F onto V. Okay. So that's F dot V divided by V dot V times V. Typically, when the quizzes used to be done in class, closed book, a lot of students used to kind of think this the opposite way as F dot F, just now that you are doing all the quizzes open book, there is no need to worry about that as long as you copy things correctly here. Okay. Just make sure that your F and V are maintaining its positions. You're finding the projection of F onto V. If you flip it, you have to flip everything. Okay, so it's the projection of one vector onto the other one. Well, you know how to find F dot V for those things. We've been doing it for a while now, so it's going to be 3 plus 2 minus 4. That's 1. Let me write it here so that you won't think that I did some kind of black magic there. So it's 3 plus 2 minus 4 divided by V dot V is just the dot product of V with itself. Okay. So V is 1, 1, 1 dot 1, 1, 1, and that's equal to 1 plus 1 plus 1 divided by 3 times the vector V. And that's 1/3 of V. And that's a pretty nice looking vector. That's just 1/3, 1/3, 1/3. So that is the answer to the first part. Find the orthogonal projection of F onto V. That is this vector. Okay. So that is, you have the vector V, which is 1, 1, 1, and a much shorter vector with components of 1/3, 1/3, 1/3 is the projection of F onto V. Not just any projection, it's the orthogonal projection, which means it's perpendicular. Now we need to find this thing here, Fn. Now that's not difficult because you have F and you have Fv now. Okay. So all that remains is to subtract those two and find Fn. So Fn equal to F minus Fv, which is 3 to -4 minus Fv, which is 1/3, 1/3, 1/3. So apart from a slightly annoying thing of subtracting fractions, this should be pretty straightforward. So this is 8/3, 5/3 or 5/3, and negative 13/3. When I prefer answers left in the fraction form than some hideous decimals, but your choice. So now we have a unique decomposition of that vector f into two parts. This plus this is always going to give you f. Okay, that is the last part here. Write f as a unique combination of two vectors, one parallel, one perpendicular. So that's going to be f equal to one third, one third, one third, plus 8/3, 5/3, negative 13/3. You might think, oh, what is so special about this? This is the only way where one of them is parallel to B and the other one is perpendicular to B. Okay, if you write any other ways in which you split f into two parts, that is not going to have that special property. Okay, that is the unique thing about this particular pair of vectors. All right. Any questions on this? So if you understood that, can you take the worksheet and finish off the remaining question, which is actually an easier one because it's an R2. So with that, you have successfully completed worksheet number 1. Okay. All right, so let's do the orthogonal projection here. F dot V is going to be -4 plus 6, which is 2. Divided by V dot V is 8, I think, 4 plus 4, times the vector V. Okay, sometimes students, they just find the value of K and forget to write V there. It's a vector. Okay, so it's some scalar multiple of that vector V. That scalar is what you just obtained using this dot product calculation. 2/8 is 1/4, of course. So 1/4 of the vector V, which is -half. So that is going to be your FV. And Fn is F minus Fv. Well, we just need to subtract those vectors. You get 5/2 and 5/2. Am I dreaming it, or is that what you're getting? 5/2, 5/2. Is it okay? Fn. There was no answer. Sometimes, I sort of get blanked out when I subtract fractions. So 2 minus -1/2 is 2 plus 1/2. 3 minus 1/2 is going backwards. Okay, so at the end of the day, when you add those two vectors, you should get to your F back, right? So F equal to, which is 2, 3, equal to -1/2 plus 5/2, 5/2. That is the decomposition of F into two components, one which is parallel to V, the other one being perpendicular to V. All right, so that is the end of section 1.3. Okay, so you need to know how to find the angle between two vectors, the condition of two vectors being perpendicular, and also find the orthogonal projection of a vector onto another vector. There are a ton of other things in the textbook in 1.3. We don't have time to go through everything, like the work done by a force and so on. Okay, I mean, you will see that in your physics class, so I'm not going to spend time here with that. So let's move on to the next one if you don't have any questions. Is this okay? Any questions about this? All right, then let's clean this up. We are still in the review part of this course, so might be going a little fast in some of the sections. So let me know if you're missing something. Okay. Section 1.4. A quick look at lines and planes. Just what we need. Okay, I'm not going to do this in its full detail because we don't need all that stuff for the rest of the summer. So we'll just look at the basics of some of the things that you have probably not seen before and might need. Okay. Lines and planes. All right, so you probably know this, that if you have the XY plane, okay, and if you draw a straight line, there are different ways of writing the equation of this line, one of them being y equal to mx plus b, which is probably the most famous form. Okay, it's called the slope and intercept form. That kind of depends a lot about whether you know the value of the slope or not. Right? When you do calculus, your we're religious about finding the slope and then putting it there. Okay. What if you don't know the slope? Another form of writing the same equation is, some of you might have seen this in high school and forgotten it. Okay. Or you can write this as ax plus by equal to c. This b and this b are not the same. Okay. This is what is usually referred as the standard form of an equation or standard equation for a straight line. It's not very popular because usually people want to think about it in terms of slope and intercept because it's easy. Okay. But the standard form for a straight line in R2 is this one. We are more interested in this form because we are dealing with vectors and trying to kind of extend that concept on to more useful things. Okay, so we are not really all that excited about this thing. Okay, that is there, that's nice, but this kind of will be more useful. Now, what is a C? And what is A and what is B? What are these things? Do you know? You write x plus by equal to c, but what are they? Here I know what they are, right? M is a slope, B is the intercept. What about this thing? Yeah.
Are they coefficients that make instead of two factors like perpendicular?
All right, so he says that it's almost correct. He says that those are coefficients that makes two vectors perpendicular. So what he said? Yep, that's kind of the right idea. Okay, so it has something to do with perpendicularity of this line with something. Okay, so let's assume that this line passes through the point. Say x naught, y naught. Okay, we always need a point on the line to make anything happen. If you don't know anything, then we can't do it. Okay? So let's assume that the line passes through the point x naught, y naught. Then you can write this as ax naught plus b y naught equal to c. Okay. Remember that we know this and this. We know this, and a and b are two constants which we are still trying to figure out. But if you know that, you know that c is now equal to these two. Okay. So we can write ax plus by equal to c, which is ax naught plus b y naught. I got rid of one of the constants. Okay. So now we just need to worry about a and b. I'm just going to bring all the terms to the left-hand side and write it in a slightly different form. So we have ax minus ax naught plus by minus by naught equal to 0. Which you can write as a times x minus x naught plus b times y minus y naught equal to 0. Now this kind of looks like a dot product of two vectors if you look carefully. Okay, got two terms multiplied here, two terms multiplied here, and added together. Okay, so if you take one of the vectors as AB and the other vector as x minus x naught, y minus y naught. Okay. This is a times x minus x naught plus b times y minus y naught. Remember, it's a scalar product. Okay. That is equal to 0. Now we have something evolving. As he said, it's something to do with the perpendicularity, right? With a dot product of two vectors is 0, that means they have to be perpendicular for 90 degrees to each other. So we have a vector that goes from the point x naught, y naught to xy. This vector is what to write as x minus x naught, y minus y naught. Okay, so if you take this as P, this is Q, the vector PQ is x minus x naught. This is just the difference in the coordinates between those 2 points. And we have another vector. This is a special vector now. Okay. Some unique vector AB, which is at 90 degrees. How do we know that? We know that because we just wrote earlier that the dot product is 0 only if they are perpendicular. Okay. So this is a unique vector to the straight line, which is perpendicular to this line. And let's denote this by n for normal. So it gives you a slightly different view of the straight line. Okay, instead of talking about y equal to mx plus b slope intercept form, this equation can be written as n dot pq equal to 0. Okay, where n is called the normal vector. To the line PQ. This is what calculus 3 does. It takes things which are usually written in non-vector form and gives it a vector notation to that, okay, and make use of things that you learned, especially the fact that the dot product is equal to 0. So the good thing now is that if you know the normal vector and if you know a point, you can find the equation of the straight line. Okay. This vector is special. Because if we know n, you could just write the equation of the straight line. This is still a line in R2. Okay, so we haven't gone into a higher dimension yet. So we need to kind of slowly transition from R2 into the higher dimension. Okay, that's what we're going to do now. All right, so let's just keep it there. Okay, we'll come back to that in a few minutes. Now, I did not say that this is not true anymore. Okay, this is still there. We're just going to focus on the vector form. Now let's do a slightly different problem. Okay, so next, consider the same line PQ. Which is going from x naught, y naught to xy. Okay. But this time it's going to be parallel to another vector. Parallel to a given vector, let's call it as v. I think the textbook uses the letters A, B, C for that, which is a bit confusing because we just used AB for the normal vector. So I'm just going to use V1, V2, V3 here. Or V1, V2 for now, okay, in R2. Once we understand this in R2, we can go into R3. So this is the picture. We have some line going from x naught, y naught to xy. And it's parallel to another vector v, which is given by those two components. The key word is parallel, not perpendicular. Okay. Now, how can we write the equation of this straight line just based on this information? We don't know anything else. Okay. Just forget about the fact that you know what a slope means and so on. You just know that this straight line is passing through the point x naught, y naught, and it's parallel to another vector v. Using the concepts that you learned yesterday and today, how can we write the equation of the straight line? Yeah.
scalar multiple.
Yes. So anytime two vectors are parallel, you can write one vector being a scalar multiple of the other vector. Okay. So this t is a scalar. It's just customary to use t as the scalar, not a k. It's up to you, right? You could use alpha there, who cares? But typically we give the name of a parameter to it. That's why we use it as a t. Okay. So PQ, which is the vector that connects P to Q, is parallel to this, which means it's a scalar multiple of the vector V. In other words, we can write this as x minus x naught, y minus y naught. Okay. The vector, which is the difference between the two components or the two coordinates there, equal to t times v1, v2. Where t is a scalar. Okay. Now this equation suddenly, if you simplify, transforms into different stages, so we need to be careful about what we name this. Okay, so this is called the vector equation of a straight line. So the vector equation of a straight line tells you the equation of a straight line in terms of two vectors. Okay, one vector is here, vector PQ, the other vector is here, vector V. Okay, nothing else. The problem with this form is that you go one step further, you get a different equation. Okay, so you can now set the x components of those two vectors equal. So we have x minus x naught equal to t times v1. And you have y minus y naught equal to t times v2. Because two vectors are equal, that means the components have to be the same. And you can solve for x and y here. X would be x naught plus tv1, y would be y naught plus tv2. Y naught means y subscript 0. So we have x equal to x naught plus tv1 and y equal to y naught plus tv2. Okay, just an algebraic simplification from the previous stage brought us here. Okay. This is called the parametric equations for the same straight line. So t is called the parameter. So the good thing is now if you keep on giving some arbitrary values for t, you can generate arbitrary points on the straight line. Okay, because we know x naught and y naught, we know v1 and v2, right? T is the only thing which is kind of waiting for input. So give t equal to 0, 1, 2, 3, or -1, -2, -3. You can generate a lot of points here on the left hand side. So helps generate xy for a given set of values x naught, y naught, and v1, v2. These things we know. That is the purpose behind each of these forms. Okay, the parametric form is to kind of generate more points so that we can understand what else is going on in the straight line. Then you could also solve for t in this case. Okay, we can try to eliminate t from this equation and this equation. So you can write t equal to x minus x naught over v1 from this equation here. Again, algebra. And the second equation gives you t equal to y minus y naught over v2. And assuming that v1 and v2 are not equal to 0, you could set this equal to each other because this is t, this is t. Okay. We have x minus x naught over v1 equal to y minus y naught over v2. Okay. That comes with the fact that both v1 and v2 are non-zero. Okay. And this is called the symmetric form of the equation. And if you took calculus 2 here at Northeastern, you've probably seen these problems when you did section 1.4. So I'm not going to do a ton of problems based on this because we need to move on to more important things. Okay, but I'll do one example just to show you how it works. But this is what the meaning of the vector equation, parametric equations, because you have two equations, okay, and symmetric equation or symmetric form of a straight line means. All right, so this is still a straight line in R2. We still haven't moved on to R3. Okay, so we are kind of at the brim of that, and we are. The next thing is to move to three-dimensional space. Okay. Any questions on this? So the important concept there is that those two vectors are parallel. That is why we had to introduce this parameter. Okay. Do a quick example. Find the vector equation parametric equations and the symmetric equation or symmetric form. Okay. A straight line, I'm just going to write line, but that's assumed to be a straight line, passing through the point Q 3 and is parallel to the vector v equal to 1, -4. Since the textbook uses the same notation for a point and a vector, you should be clear about what you're looking at. Okay, so that's a point, and this is a vector. Some textbooks use those sharpened things for vectors. Here we use the same thing. So based on the context, you should be able to understand the first one is a point, the second one is a vector. All right, let's quickly do this. Nothing fancy about it. You have both the things you need. Okay, just plug it in, right? So the vector equation is I'm staying on this side because it's easy for me to see. Okay, so there's a lot of blank space on that side. All right, so it's going to be x minus x naught is 2, y minus y naught, which is 3, equal to some scalar or a constant t times 1, -4. You could probably do one more simplification. Some textbooks do it. Okay, you could write this as xy. You can just bring the 2 into this one and 3 into that one. Okay, so it's going to make it look like 2 plus t and -4 plus 3t. That looks weird. No, -3 plus 4t. That way, it looks like a vector equal to another vector here. Okay. So some textbooks, they just stop it here, some stop it here. Doesn't matter for me. Okay. So both of those are vector equations for the same line. But don't simplify any further because that will become a parametric equation. Okay. So we should stop there if the question is just to find the vector equation. But we're almost there, right? The parametric equations are x equal to 2 plus t, y equal to -3 plus 4t. So if somebody is asking you, give me 10 points on the straight line, just sit down and give 10 different values for t. Okay, t equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You generate 10 points on that line. And the symmetric form or the symmetric equation so we're solving for t from each of these. Okay, so from here you get t equal to x minus 2. And from this equation you get t equal to y plus 3 over 4. So if somebody is asking you, is the point 1, 1 on the straight line? I don't know, right? But you could plug it in here. Is the point 1, 1 on the straight line? 1 minus 2 is negative 1. 1 plus 3 over 4 is 1. Negative 1 is not equal to 1. So the answer is no. Okay. So this can be used to check if any arbitrary point is on the straight line. In particular, if somebody wants to know, is 0, 0 on the straight line? Answer is no, because you cannot have negative 2 equal to 3/4. All right, so keep this in mind, okay? I wouldn't say that this is super important, but you might see a few things periodically which refers to right vector equation. Okay, so you should know what it looks like. But what we're going to do next is super important. Okay, so just try to remember this for the time being, and let's see what we can do with this. Before that, do you have any questions about the vector equation, parametric equations, or the symmetric form for straight line? Are the people online, are they all still there, or are you kind of gone away from there, letting me talk? You know, just unmute and say hi to each other, maybe, just to break the silence. You know. All good. All right. That's 1 out of 13. I know it's a weird way of teaching and studying, so. All right. Good. Okay, now, still in 1.4. Okay. Let's move on to R3. Again, R3 is your XYZ space. So suppose you're given the point x naught, y naught, z naught. Earlier we talked about x naught, y naught, and xy. And if you have n, which is perpendicular to this, we just talked about it 10 minutes ago, right? We can write n dot pq equal to 0. So this is for all the points on the straight line which is perpendicular to this vector. Okay, and this is in R2. Now we can ask a corresponding question in R3. Okay, given a point x naught, y naught, z naught, what will be all the points x, y, z, such that if you take the vector between these two, it's perpendicular to a vector ABC in R3. So same kind of situation, right? You had a straight line and a vector perpendicular in R2. Now we have a set of points. Okay, now this could be everywhere because now in three-dimensional space, not just on a straight line. Okay, this could be here, this could be here, this could be here. Okay, so what is the set of all those points going to create this perpendicular to here? It generates a plane in R3. Okay, it was a straight line in R2, so you have to just keep on moving on the straight line. Now we have more freedom here. Okay, so it generates a plane. So the set of all points x, y, z, which is x, y, z, such that this vector pq is perpendicular or normal. Okay. To this vector n equal to ABC. It's no longer a line because you can walk around it. Generates a plane in R3. So we are lucky today that we saw this straight line today, not 2 days ago. So we can easily kind of refer back to what we were doing. Okay. So just like you had n dot pq equal to 0 in R2, we can write an equation here, same equation now in R3. That is what the equation of a plane looks like. The equation of a line looks like n dot pq, but that is a line. Okay, you cannot go left or right there. This one, if you know the components of the normal vector n, okay, it's a very special vector because not all vectors are going to be satisfying this equation here. Okay. Dot with any vector that is on the plane, and that should be equal to 0 at all times. Okay. So this is the standard equation but of course it looks too cryptic to us, right? If you say m dot pq equal to 0, what does that mean? Okay, so we need to kind of expand it out and write it in a more civilized form so that it's useful for us. I hear a humming sound. Is it from a microphone or? So n equal to ABC, and let PQ be the same notation as you wrote there. Okay, so P is x naught, y naught, z naught. So we know this point. Okay? We have to know something to start the problem. So we know this point is part of the plane, and Q equal to x, y, z is any point on the plane arbitrarily. Then the vector PQ is x minus x naught, y minus y naught, z minus z naught. So if you take the dot product of those two vectors and set that equal to 0, okay, you set a times x minus x naught plus b times y minus y naught plus c times z minus z naught equal to 0. Now, if you look back to what we wrote for that straight line, using the normal vector, you will see that it's just an extension of that equation here, right? This first two terms would have represented a straight line with just x naught, y naught on that line. Now that we have a third component, all it does is just extending that line into a plane in R3. Okay, so that is the jump from 2 dimensions to 3 dimensions. You've got a lot more freedom now, but in terms of the algebra, it's just a very simple addition here. Okay. All right. So this n is called the normal vector again. And it's the most precious vector you have learned today. Because if you have that, you have the answer. Okay, the question is, what if you don't have it? Okay. But for the time being, let's assume that you know it and we are able to do these problems. So before we do any problems based on this, do you have any questions on any of these concepts we talked about here? All of you should be able to write the equation of a plane. Okay, that is a basic requirement of calculus 3. And you'll get a chance to do it on Thursday's quiz, so don't worry. So a quick example. Find the equation of a plane, or write the equation of a plane. Passing through the point, I'm just going to be lazy and writing through like this. Okay. Through the point 1, -2, 5. So that's a point, and is perpendicular to the vector 2, 4, 7. So again, it's a very straightforward question because everything is kind of given to you on a nice plate, so you just need to eat it. Now, if you don't know the point or a point, you cannot do anything. Okay. If you don't know the normal vector, we will see there are different ways of doing it. So in this case, everything is given. So this is your x naught, y naught, z naught. And this is your ABC. So we have a times x minus x naught plus b times y minus y naught plus c times z minus z naught equal to 0. Okay. That's going to be 2 times x minus 1 plus 4 times y minus -2, y plus 2 plus 7 times z minus 5 . Remember, you're writing an equation, which means there should be an equal to sign with something on both sides. Okay, in this case, that must be equal to 0. Don't just write like this. Okay, this is not an equation. In some cases, you might be asked to simplify this a step further, and you just need to distribute this, and there's going to be 2x plus 4y plus 7z. Then you have a bunch of constants here. You have -2 plus 8, which is plus 6, minus 35, which is minus 29, equal to 0. Okay. And this is usually what some textbooks refer to as the ax plus by plus cz plus d equal to 0 form. No matter which form you write, make sure that the ABC, the components of the normal vector, are always something you can recover easily. So A is 2, B is 4, C is 7. Okay, you shouldn't lose that part. Okay, that is the key thing about this whole equation of a plane thing. Okay. So it could have all kinds of other things going on. At the end of the day, the normal vector should remain pristine. All right, let me just quickly mention this. We talked about the vector equation of a line in R2. Now that we are in R3, we can just write a quick extension of a vector equation of a line in R3. So here the context is the following. We have a straight line in R3, okay, not in R2, and it's parallel to a vector in R3. So this is x naught, y naught, z naught, and this is x, y, z, pq, and this vector is v equal to v1, v2, v3. So those two lines are parallel. So, just like we did earlier, you could write the vector PQ equal to some parameter t times the vector V. If you understand R2, you can do anything. Now you can extend it to R3 or R4. Okay, you are the boss. So this is x minus x naught, y minus y naught, z minus z naught equal to t times V1, V2, V3. And you can still do all the other things. You can write it in the parametric form, symmetric form. Okay. Once you get the idea, the rest is just algebra, which at this stage you should be able to do easily. What you should not forget is that this vector is parallel to this line. Okay. And I'm sure if you did calculus 2 here at Northeastern, you did a few very easy questions based on this concept. You know, you can solve 10 points in 5 seconds if you know what you're doing. So we'll do a few of those. I think it's in the worksheet. Let's do that quickly. Okay. This is worksheet number 2 now. On Canvas, under modules. Let's do 1, 2, and 3. Okay, in that order. I was going to say let's do number 3, but let's also do 1, 2, and that way we'll be kind of ready to jump into the next section after this. So we'll just do 1, 2, 3, and we'll be done for today. This is worksheet number 2. Okay, and if you look at the bottom of that worksheet, it has written quiz 1 on Thursday, covers worksheets 1 and 2. So the rest of worksheet 2 will be done tomorrow. I'll usually try to finish all the quiz material by Tuesday, but this is the introductory chapter. That's why I'm kind of pushing it to tomorrow. Okay, but it should be okay. All right, can you start with the first problem and see? So for the online crowd, this is the file we are looking at. Okay, hopefully. question is not asking you to simplify it, so you can just leave it in that form. That should be okay. When did math become so easy? Just plug in numbers, you're done. This is what calculus 3 is about. Okay, any questions on that one? That should be just a mutation of the previous example up there. Okay. Find a non-zero vector, non-zero normal vector to the plane 3x minus 2y plus 5z minus 12 equal to 0. Write that right. Now, this shouldn't take any work. Okay, you should be able to just look at that and tell me the answer. Let me see if anybody online can kind of quickly give me the answer to this question. Find a vector normal to this plane. Now, don't reinvent the wheel or anything, just 3, negative 2, 5. Okay, that's it. So just look at the coefficients of your x, y, and z with the sign, of course, and the normal vector should be 3, negative 2, 5. What else should we do there? Nothing. The question is not asking you to do anything else, so don't waste your time. Now, number 3 is the one I want you to kind of think about and do. And this is the one I said, it's a kind of those routine questions to do in calculus 2 here as a gift in your final exam, because it's so easy if you know what you're doing. Okay. You're given a point and it's perpendicular to the plane. Okay, so you have to kind of connect a few concepts there. Not too bad, but you have to think a little bit. I forgot to tell you that on the days or on the Thursdays I give quizzes, the lectures are going to be shorter. Okay, so the quiz is 50 minutes, so I will teach only for around 40 minutes on Thursday so that you don't spend any more time with me than you need to. And on the days in which we have tests, of course, there won't be any lecture, so that way things are balanced out. Okay. Otherwise, you will think that I'm forcing you to spend too much time with me. Number 3. Let's draw a picture for this, okay, because you have to kind of make the connection here. You're given a line that passes through the point 3, 5, negative 2. And it's perpendicular to the plane. So the plane is sitting like this. Okay, the line is perpendicular to this. And for some reason, you are given the equation for this plane. I don't know if we could do anything with this thing, but let's see. You have to find the vector equation of this line. Okay. Remember, the vector equation of a line needs 2 things, a point and a vector parallel to the line. Okay. So that's where you have to kind of connect the dots. All right, let's see who is going to help me here. Anybody here wants to suggest anything? Yes?
So you have a vector that is normal to the plane using the coefficients.
Yes, so the coefficients of these will give you the normal vector to the plane. Okay. 2, 5, negative 7. How does that help us?
Line that line is parallel or perpendicular to the plane goes to line through vector set parallel.
Yes, so this line is perpendicular to this plane. Okay. This line is perpendicular to this plane. So by construction, they are parallel. Okay. So this is parallel to the line that we need. Let's call this a line L. Okay. Parallel to L. Okay. That is just by making use of the fact that both these things are perpendicular to the same plane, they have to be parallel. Okay. Just like if you put two lines perpendicular to this floor here, they have to be parallel. Okay. So that's all we need then. This is your V1, V2, V3 for the vector equation of the line. That is your x naught, y naught, z naught. So the vector equation of L would be x minus x naught, y minus y naught, z minus z naught equal to, remember these are parallel, okay, so it's going to be some parameter or some constant times this vector which is parallel to that line, which is 2, 5, -7. Or if you want to write it in a slightly more satisfactory form, you can write this x, y, z. But there are different ways in which you can kind of finish off this. So this is, you can bring all these numbers to the right hand side and write as 3 plus 2t, 5 plus 5t, and -2 minus 7t. Not very picky about how you write these things as long as your concept is correct. Okay, this is the key thing I want you to observe here, that the normal vector from this plane is parallel to that other line. All right, so I think that will be a good place to stop, and we will look at how to find this normal vectors tomorrow. Okay, it's a very important lecture because we're going to do cross product of vectors and area of triangles and so on. So please don't miss it. And in the meantime, have a nice rest of the day. You have 50 minutes, 50 minutes to write and upload. This week's quiz will be pretty easy, just dot product and cross product. Let's.
Thank you.
There are bad things to come later, but let me not scare you now. All right, let me stop recording then.